Yeah, okay, all right. All right, hello everyone. I hope that you're all doing really well. Welcome back to Comp 3430 Operating Systems. I was thinking on my way from my car to my office today that you know, the weather has been feeling really nice. I know I talk about the weather a lot, but this is just like this big thing in my head, the weather. And I don't know if this is a Winnipeg thing or if this is just like a human person thing. I don't know the difference. But I was thinking on my way from my car to my office today that it's feeling like springtime. It really is feeling like springtime. But I also haven't heard any geese yet, and that tells me that it's not springtime yet. As much as I hate geese, as much as I hate geese being around because they're just like giant, annoying bastards, if they're not here, it's probably not springtime yet. And so now I'm feeling a little worried that it's going to get cold again, but I don't know. I'm just hoping that I hear a honk when I'm going back to my office today. I hope that you've all had a good weekend. What I want you to be able to do by the end of today's lecture is I want you to be able to write code that uses pthread mutex lock to protect a critical section. So at the end of last class, the state that we were in was that we had taken a good look at this code that was called list insertion.c. And this code was designed to have a race condition or a critical section where when we are inserting nodes into a list, where we're trying to insert a node after another node, where that one node that we're inserting after is the shared resource. We'll take a look at the code again, so don't worry if you forget everything. The problem was that under certain circumstances, we could lose nodes because there's a critical section here. And so the code that we wrote never crashed. There was never a segmentation fault. There was never a case where we were getting, you know, bus error, core dumped. It always just worked. And when we had a very small number of threads, when we had like 100 threads or fewer, it always seemed to work correctly. And it wasn't until we got to that point of having tens of thousands or hundreds of thousands of threads that we actually started to see these circumstances where we have fewer nodes than expected in the list in the end. What I want to do today with this is I want to think a little bit about how to place locks in this code sample to prevent this from happening. There are a couple of what I'd call technically correct places to put the locks, but each of these choices has some performance characteristics that are going to change how this multi-threaded program works and kind of limit how much concurrency there can actually be in the code that we're looking at. So I want to spend some time taking a look at those options and then thinking about the kinds of consequences that we get for picking the wrong but technically correct place to put our locks. The other thing that I want to start doing today is I want to be able to identify code protecting a critical section that would result in deadlock. So deadlock is this special case of a concurrency bug where we have multiple threads of execution and they are getting into a state where they cannot proceed. They are just unable to proceed past a certain point, and it has everything to do with locks. We're trying to acquire something and we're unable to proceed past that point because of a bunch of conditions that are going to be held for this to happen. So I want to be able to identify a critical section where we're using locks and it could result in deadlock. I want to identify that. And then ultimately our goal is to begin proposing solutions that would avoid or prevent the deadlock from happening in the first place. The best solution here is just don't use locks. The worst best solution, the solution that will be functional but will not do what we want, is just not use locks at all. But we kind of can't do that. So we'll have to think about how we can accomplish this. So first things first, let's take a look. Again, I want to take a brief look at listinsert.c, and I want to take a brief look at the state that we were in that would result in this unexpected situation. So I've got, this is that thread management repository. There's a couple of things that we're going to look at today in this repository. But the first thing I want to look at is the list insertion.c code here. So the code that we had and the critical section that we identified was entirely within actually just these two lines, lines 27 and line 28. And the issue that we saw with this, and just to confirm quickly, is it big enough at the back? You can see it, okay, awesome. The problem that we have with this is that this insertion operation, where we have these two statements, it's not atomic. It's not an atomic operation. The issue that we were seeing, and this happens really rarely and only once we have massive amounts of concurrency, is that one thread is going to execute this line right here. So we're going to set the next of the node that we're trying to add to this list to be the next of the node that we are inserting it after. A thread of execution can be interrupted in between this line and this line. And another thread of execution can complete both of those things. And what that results in is a situation like this, where, whoops, open critical section.png is what I'm trying to say here. A situation like this, where we insert partially some node that we're trying to insert, then lose control, the second one takes over, and then fully and completely inserts the node that it wants to insert. And then we come back to that first thread of execution and finish up. So we do the complete the insertion of the next node. By completing the insertion of the next node, we're changing this previous pointer, the thing we're inserting after, to be the new node for that thing, and we're losing this other one. So we wind up in this situation where we've got these nodes that they're like sort of attached to the list, in that the node points at something that's in the list, but nothing points at it. And so as far as our list is concerned, that node doesn't exist. This kind of means that we're leaking nodes, and that kind of means that we're leaking some memory. We can never recover that memory because we don't know that it's there. We can't point at it. We don't have anything that's pointing at it anymore. But importantly, we've lost some data. I'll emphasize again, the list is valid. The list is still valid. As far as our code is concerned, we are able to iterate over this list and we will not crash. This list is a valid list. We're just missing data that we had originally intended to insert into this list. So what we need to do is we've got to start adding some locks to this code. We need to prevent concurrent execution of this critical section. We need to enforce mutual exclusion here. We need to try and make this operation atomic somehow. And there's a bunch of different places that we could try to add the locks for this thing. And so what I want to do here is I want to ask you what you think in terms of where these locks should go. And so I'm going to pop back here, and I've got a QR code. I'll hold this up for a few seconds. My question is going to be order these statements of which one we think is the best, and we'll try to explore each of these things. Okay, so I'm going to pop over to the Mentimeter now. So I got 4 options here, and I'm not even going to tell you what I want you to think about. I just want you to think about something and then order them. We've got file scope lock variable. That was the approach that we did with the textbook sample that we were looking at. A function scope lock variable. Putting a lock on the list itself, so the head of the list, or putting a lock on the node we're going to change. So I'm going to leave this up here for maybe 20 seconds to let you do some voting, and then we'll take a look at each of these. Okay, I'll leave this up for 5 more seconds, and then we'll start taking a look at these. We'll take a look at them from the bottom up. All right, okay. So let's try this out. I don't think that I'm actually going to write this code to run it. I don't think I'm going to write this code to run it, but I will put some comments in the code to try and think about where we could be putting these things. So at the very bottom here, we've got a file scope lock variable. So the way that this would look is beside our node head, we would add a file scope lock variable. So something like pthread mutext head or insert lock, something like this. So this is going to be a lock that we would put outside of everything else. And we're going to have to acquire the locks here. I'm just going to assert that we must acquire the locks in this code. We must acquire them in the insert after function itself. So acquire a lock, and then release the lock. Okay. So I'm going to think about this for a second. I want us to think about this for a second. If we have exactly one lock at the file scope, and I'm really quite happy to see that this was at the bottom. If we have exactly one lock, then every thread of execution has to share that lock. Every thread of execution has to share that lock. So if I've got 10 threads of execution, then all 10 threads are going to have to share that same lock. Thread 1 will acquire the lock. It will do its insertion operation, and it might get interrupted in between these things. And then it will release the lock. Then thread 2 will acquire the lock. And let's say that thread 2 gets interrupted after line 29 here. So it's in the middle of it. And thread 3 starts to get to execute. It gets to this point where I try to acquire the lock, but it can't. And so it gets blocked. It gets stuck here. And then eventually thread 2 gets to take over again, and it will finish up. It will insert after next, and then it will release the lock. And then thread 3 gets to go. And then thread 4 gets to go. And then thread 5 gets to go. And then thread 6 gets to go. And the problem that we have with this is that if we've got a file scope lock, we're pretty much turning this into a sequential operation, regardless of how many threads we're executing. Every thread has to wait for the last thread to finish, every single thread. But it's worse. It's worse than that. If I can make any number of lists, so I have a make list function, and I don't have a file scope head. Think about this for a second. I don't have a file scope head. This means that only one thread of execution will ever be able to insert a node at any time in any list. Just one, just one. It doesn't matter if they don't have, they're not trying to insert into the same list, they're just gonna have to wait for one thread of execution to finish. So while this is technically correct, it will result in no nodes being lost because we've turned this operation into an atomic operation. It means that we can never have any concurrency on insertions. We can never, ever have any concurrency on insertions. And that might be okay. That might be okay. Like, depending on the kind of problem that you're working with, that might be an okay situation to be in. But we're not going to be able to do any kind of concurrent execution of this function. Does that make sense to everybody? We're okay with that? Okay. So let's pop back to the Mentimeter now. Our next one is to have a function scope lock variable. A function scope lock variable would look like this. pthread mutex t insert lock. Is this consistent with what everybody's thinking about in terms of a function scoped lock variable? Take a second to think about what we've got here. I'm going to open up some other code. I'm going to open up this code right here. This is our textbook sample modified A. And I made a change to this after the fact, so I'll point out the change that I made after the fact. The change that I made after the fact was that I renamed the file scope variable here. The result of this was that we added this file scope variable called counter, and we counted up to 1,000,000 in each of the threads of execution that we had. And then at the very bottom, in our main function, we printed the value of outside counter, but that was still just 0. It was still just 0. It was still just 0. And it was still just 0 because we never actually did anything outside of our function. This variable was a thread local variable, so we definitely got rid of our race condition, and we got rid of the critical section, but we never got the correct result as output from our main function because we never modified any shared state. But if I come back here, this is really similar to that idea. This is now a thread local instance of a lock. This is a thread local instance of a lock. That means you get a lock, and 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 we can all hold on to our locks, and we can do whatever the hell we want to this list. We can make any change that we want to the list. This is a thread local instance of a lock. Every thread is going to get its own lock to hold. That means that when I try to acquire the lock, I will always get it. I'm always going to get the lock that's only available to me. I'm the only thing that can ask for this lock, so I'm the only one that gets it. Any lock, any thread in this case, trying to get the lock will always get the lock. This thread is the only thread that knows about the lock. So if we put this file scope lock in here, we still have a race condition. We still have a critical section. We haven't actually removed the issue that we've got here. Every thread gets its own lock. Every thread is guaranteed to acquire the lock. And every thread is going to just execute concurrently and will eventually run into the same kinds of problems that we were having before. Does that make sense to everybody? We're all okay with that? Okay. Let's take a look at the next option here. On the list itself, so in the head of the list. I'm going to actually go back to the one that we did here. Add a file scope lock variable, or add a head scope lock variable, add something to the head of the list here. This, in this case, is effectively the same thing. It's effectively the same thing, but I'm going to change this a little bit. So I'm going to change this just slightly. I'm going to say that, and I'm going to change this in a way that it's not going to compile immediately. I'll fix it up after class, but if I added this, typedef struct node, typedef struct list, sorry, list, and I'll put this below my node definition here. and I say node pointer head, and I say pthread mutex t list lock. Or I'm even going to go as far as to say insert lock. If I add this lock here, we will have solved our problem. We will definitely have solved our problem. But we're now limiting concurrency on the list itself. The problem that was identified, that I identified with our file scope variable, was that we're limiting concurrency for all lists. We can only ever insert one thing in any list concurrently, no matter how many lists we have. If I put this list lock or insert lock inside of this list type, so lock my head or lock my list, now I'm going to be able to have any number of threads inserting to different lists concurrently, and that's totally fine because it's not a shared resource among those threads. The problem now is that if I've got a node that is trying to be inserted after the head and one that's trying to be inserted after the tail, they cannot execute concurrently if they are completely different nodes, if they're very, very separate or very, very far apart from each other. So this will prevent concurrent execution of threads within a single list, but allows concurrent execution across different lists. They aren't shared resources, so that's okay. But now we can't insert into nodes in the same list concurrently, even if they are very different from each other. So head and tail cannot be inserted after concurrently. And that, again, that may be okay. That may actually be okay. That might be totally okay for the workload that you have with this list that you're working with. And so the last option that we have here is on the node we're going to change. And so that means that I'm going to go back up here, and I'm going to say that I want to put a lock right here, pthread mutex t insert lock. This is going to give us the finest grained lock, but now every node has a lock. So if I'm going to insert into a list that's got 100,000 nodes in it, I'm going to have 100,000 locks that I have to keep in here. And so now we might have to worry about memory constraints. Practically on systems like this one, we do not have to worry about memory constraints for 100,000 locks. This is going to be like a few K of data that we're going to be working with ultimately. But on smaller systems, if you're working on embedded systems, you might have to care about something like this. So if we put the lock here, then we can have maximum concurrency. Different nodes in the list can be inserted after concurrently without having to worry about losing nodes. But we have 100,000 or n locks that we have to keep in the list to be able to do this. All of these options, with the exception of the file scope lock, are correct implementations. They will all result in a list that never loses any nodes, but they have different characteristics that we kind of need to consider when we're going through and implementing this stuff. All right, okay, that was thrilling. That was really, really exciting to step through all this stuff. But I want to make sure that we're thinking about like where we could put these. The example that I started with over here was pretty much blindly like, we have this file scope shared variable, so we must have a file scope lock to be able to prevent concurrent execution. But with an example like this one, where we're working with complex data structures, complex, like it's a list, it's a complex data structure, but there's many different places that we could put this that will result in a correct implementation. but have different kinds of characteristics attached to them with regard to things like how much concurrency we're able to get out of operating on this thing. Does anybody have any questions about this before I move on to the next step for today? Okay. All right, awesome. All right. So what I want to do next is I want to start talking a little bit about deadlock. So we have just seen a kind of concurrency bug, and we've been trying to resolve that kind of concurrency bug. The concurrency bug that we're looking at in our threaded list insertion code is we might lose data because different threads are trying to access and mutate the same resource, and their mutations or their changes are not atomic. They have to read and then change something from that thing, and they might get interrupted in different places. We were able to solve problems like that by adding locks to our code. And if we're adding locks to our code, then we're going to run into other kinds of concurrency-related issues. The main one that we're going to be thinking about in this course is deadlock. And deadlock is a situation where we have threads of execution that are running concurrently, and they try to acquire locks, but get into a state where they're unable to proceed because of a set of conditions that must hold. The 4 conditions that have to hold for a deadlock to be able to happen are mutual exclusion. We'll talk about each of these in a moment. Hold and wait, no preemption, and circular wait. These are the 4 conditions that must be met for a piece of code to be able to get into a deadlock situation. But I want to be really clear that deadlock is not guaranteed to happen if all 4 of these things hold. It's just possible for it to happen. It's actually quite rare for it to happen, but it's possible for it to happen. That's the only thing that we're able to say about this. Okay, so mutual exclusion. Mutual exclusion is that threads claim exclusive control of resources that they require. So a thread is able to grab a lock. The analogy that I have for this is that when we are in a place like, so let's say, how many of you have been to Across the Board? Okay, there's a set of bathrooms there, because of course this is going to be talking about bathrooms. Yeah, absolutely. This is 100% what we came to talk about operating systems for. The bathrooms there they're gender neutral bathrooms, so it's just like there's doors on the wall and you go into the bathroom and you are in the bathroom by yourself, right? Mutual exclusion here is when I go into the bathroom and lock the door, nobody else is coming in. That's it. I hold this resource now. Nobody else can use it because I have that resource. Nobody else is allowed to come in because I've locked the door on this thing, so nobody else can come in. I'm able to claim exclusive control of a resource that I require. In code that we're thinking about, this is a thread is able to get hold of a lock. It acquires a lock and it's able to enter a critical section. In the code that we have over here, that means that a thread is able to get to line 67. It acquires a lock and it holds it after it has passed that, and no other thread is going to be allowed to enter the critical section. Any other thread that tries to acquire that lock will get stuck. It's going to block and it's going to wait on the line just above it on line 66, where it's trying to acquire that thing in the first place. One or the other, but not both. Mutual exclusion. Hold and wait, our next condition for deadlock, is that threads hold resources that are allocated to them while they're waiting for additional resources to acquire. So I am able to acquire a lock, and I want to acquire another lock. This is now an important thing to note. It's not just one. there are now multiple things, 2 or more things that I'm trying to get hold of, and I'm able to get one of them, and while I'm waiting for the next one, I'm just going to hold on to this thing forever. In order to be able to write on my tablet here, I need to be able to get access to this pen. Once I have access to this pen, I'm going to hold on to it. And here, you can have this, okay? It's not yours forever. You can have that. I'm going to hold on to this pen, and I'm going to say, hey, can I have that? And you're going to say no. Can I have that, please? Okay, but I'm just going to hold on to this. I'll just wait here until you're done with it. Can I actually have it, though, please? Okay, so I'm just going to sit here and hold on to this thing. I'm going to sit here and hold on to this thing, even though I can't get the next thing. And I'm just stuck. I am holding on to this, and I'm waiting for the next thing to become available. That's hold and wait. Mutual exclusion, I hold this, none of you can take it from me. Hold and wait, I'm holding on to this, I'm waiting for this other thing, and I'm not giving this one up while I'm holding on to it. No preemption. Resources, once they're acquired, cannot forcibly be taken back. I'm holding on to this pen. You can't have it. You can't take it from me. This sounds like a, fight me for it sort of thing, but no, you just can't have it. Once I have it, you can't take it from me. In code, this is more like once I'm able to enter this critical section here, once I've been able to acquire the lock, the operating system has no way to get the lock back from me. As far as our OS is concerned, it actually doesn't even know that I hold a lock. So there's no way for it to say, give that back to me. I'm going to take it back. Mutual exclusion. I can acquire the lock, and nobody else is allowed to acquire it. Hold and wait. I've got the lock, and I'm waiting for something else. I'm not going to give this thing up. No preemption, I've got it. You cannot take it away from me, possibly because it's not possible for you to take it away from me, possibly because I'm not going to be willing to give it up in the first place. Once I've got it, you cannot take it back from me. And the last one is circular wait. We've got some situation where I'm able to take a lock, getting mutual exclusion. I'm able to hold that lock while I'm waiting for something else, and nobody else is allowed to take it from me. But now there's 2 of us, and we're both waiting for the opposite thing. So I'm going to give this back to you again. You've acquired that. You hold it by yourself. I've acquired this. I hold it by myself. I see that you have that, so I'm just going to hold on to this and wait. And you see that I have this, so you're just going to hold on to that and wait. But we can't take it from each other, and we're not giving them up. And we're stuck. We cannot proceed. We're both pointing at each other and waiting. Yeah, thank you for participating. Yes, thank you so much for participating. Now we need to bring Spider-Man costumes next time. We're both sitting here waiting for the other one to give that thing up, but we're never going to proceed. We're stuck. We are deadlocked right now. We can't proceed. We're stuck forever waiting for this stuff to happen. Thank you for participating by holding on to my tablet for me. I want to take a look at some codes, and my goal for this today is really just to take a look at this code. I don't want to run it. I'm not even interested in trying to identify whether or not this code can deadlock today. My only goal for us today right now is to have a better understanding of what this code is doing and what it's trying to accomplish. There's a bunch of setup involved in contriving this situation in the first place, And I can't even promise that I'll be able to demonstrate deadlock happening in this code because it's kind of a thing that's just like, it happens rarely. There has to be a bunch of circumstances happening all at the same time to get us into the state of deadlock where we're not able to proceed. But I'll remind you that many of you have probably already seen deadlock in your shells where you've got some code that's trying to write to a pipe or trying to read from a pipe and it just gets stuck. All of these conditions have held. I would like you to think about that. If you've seen this situation happening, I'd like you to think about this. And we're not talking about threads here. It's all about shared resources in the form of pipes and stuff. So this code is in this file that's called deadlock.c. It's in the thread management repository. I'm going to quit this code. I'm going to quit this code. I'm going to open up deadlock.c, and I'm going to zoom in here, and I'm just going to look at this, because this is the only thing that I want to look at right now. This is an example where we are setting up super contrived situation of transferring money between accounts. Got bank accounts, and I want to be able to take money from account A and put it into account B. I want to be able to take money from account B and put it into account A. So I've got a bank account that has a balance. You probably shouldn't use just integers for balances, but that's an exercise I'll let you figure out on your own. Every account here has its own lock. This is good. I want to be able to make transfers between completely unrelated accounts and not have to worry about concurrency. You shouldn't have to wait to transfer money to your friend because I'm transferring money to my mom. You shouldn't have to wait for that to happen. We should be allowed to do these things concurrently. We've got this structure. This is the structure that we're going to pass to our threads, and it kind of looks like the insert operation that we were doing with the list insertion code. I've got two accounts. One of them is called from, the other one's called to, and I'm transferring some amount between these things. There's a create bank account function here. This is our constructor function. The constructor function is initializing our bank account, and it's initializing our lock. I've put this alternative way to initialize a pthread mutex lock. Last time we did pthread mutex lock equals this pthread mutex initializer, but the other way to do it is to pass it to pthread mutex init, and then it returns this new account. This deposit function now, this is the code that's doing the transfer between the two accounts that we've got. And so the structure of this is that I want to start by acquiring a lock on the from account. I want to acquire a lock on the from account before I do the transfer because I want to make sure that it has enough money to do the transfer before I actually do the transfer, and I don't want somebody else to change the balance of that account after I've started to do the transfer. I don't want to have overdraft support for this thing. So I want to take hold of the lock on the from account. I want to test to see, does this account actually have enough in it right now to do the transfer? And if it doesn't, I want to unlock. I want to release the lock that I've held so that other people can do transfers between this account and some other account, and then I'm going to return null after this. If I am able to confirm that the from account has enough money in it, then I want to start acquiring the to lock. So for the accounts that I'm putting this money into, I want to be able to do that. And then we've got these two statements here, minus equals and plus equals. Remember that this is ultimately going to be like 6 instructions. So we want to make sure that this is fully locked because we're going to have to do load add store and load add store for each of the different accounts that we've got here. Once we've done the transfers, then we can unlock the two things and then we'll release the pointer here. This is the thing that was passed to us. This is the structure that was passed to us. This was dynamically allocated in the main function. The create transfer function is a constructor for the transfer object itself. And then here is our main function. Our main function is setting up 2 threads of execution. We're creating these two bank accounts, account 1 and account 2. The total balance for both of these is 1,000 at the beginning. We're making this transfers between the two accounts. The transfers that we're doing are, I want to take money from account 1 and put it into account 2. I want to take 100 units of money and put it from account 1 to account 2. And the other one here is, I want to take 100 units of money and put it from account 2 back into account 1. So the net result of this should be that our two accounts have the same balance that they started with because we're just transferring this money back and forth between the two of them. We create the threads to do the transfer, we wait for the threads to do the transfer, and we print out their balances at the end. I'll compile this, and I'll run it, and it works. It does what we hoped it would do. It results in the same balance being in both accounts at the end because we've just transferred the same amount of money between these two. My question about this, and we will look at this next class, is can deadlock happen? Here's the function where we're acquiring locks. There's nowhere else that we're acquiring any locks. So I will straight up point at this and say this is the only place where deadlock could happen. This is the only place where deadlock could happen. Can deadlock happen? Don't want you to answer right now. We will look at this next class, but this is where we're going to start next class. Can deadlock happen here? And to do that, we're going to start taking a look at the different conditions for deadlock for that. I will make sure that, that this code is up on the repository. But the last thing that I wanted to do today is I promised that I would have time for questions for the assignment. And so I have some time set aside for questions about the assignment. There have been lots and lots and lots of good questions on the forum, so please check that out if you haven't been taking a look at that, but I'm very happy to take some questions right now. You're also welcome to ask verbally. You don't have to type it all out if you don't want to. And if I need to refresh the page, please let me know. For input redirection, do we have to read contents in mem through the file descriptor and then close standard in file descriptor? All right. So for input redirection, you can close the standard input file descriptor, I guess, but you don't need to. If you close the standard input file descriptor, it might remove it from the open file table for the process that you're about to execute. So you probably don't want to close the standard input file descriptor. I would say that once you've done dupe 2 on that, so like you've read from the file system into memory and then you've duplicated that file descriptor into the location for standard input, that you should just leave it open and let the process or the program that you're going to run after that be responsible for closing it when it's finished. Do we have to be able to launch process for any script file given? So the root image that I'm giving to you is an example of a root image. It's possible for me to put other programs onto that, and then you should be able to run different programs based on what's there. So there shouldn't really be any hard-coded stuff for a specific program here. The only places where you would have hard-coded stuff is for the built-in commands. So for ls and cd and pwd, those should pretty much just be like hard-coded, check to see if this is the first command, and then do something in your shell based upon that. But it's possible for the root image that that we're going to be working with the graders to have other stuff on there. Does input redirection just switch standard input so arguments from a file can be read even if those args make no sense in the command context? I'm not sure I understand this question. So like, I'm going to pop open my terminal here, and then maybe what I'll ask is if the person that's asked this question can just nod emphatically at me. So do you mean that if I do something like cat deadlock.c and then deadlock.c like this, is that the question that's being asked?
Oh, I was like more referring to, say you input redirect. I'm just wondering, when I'm thinking of cat, I'm thinking of your implementation of cat in NQP. Is that the same cat being run?
No, so it's not actually using the cat in NQP. This is actually just using the program cat.
Yeah, so like an argument that wouldn't make sense.
Yeah.
No file parameters. You pass in cat input redirect to say hello.text. Does that just pass by as an argument and it prints it? Like,
Okay, so I'm gonna pretend that we're in the root volume here, and I'm gonna say cat hi input redirect hello.txt. Is that kind of what you're thinking?
so if you do cat hi, it'll just won't run, right?
Yes.
But isn't cat input redirect hello.txt just the same thing as cat hi?
No.
No.
So what this command does is it's saying, I want you to open a file. Cat is going to try to open a file. Like it will try to run the system call open on a file that's named hi. If I run this hello.txt, cat is just going to, it won't try to open anything. It's just going to immediately start trying to read standard input file descriptor. And so whatever the standard input file descriptor has as a reference to the file, it's going to read the contents of that. And in the case of hello.txt, I would expect it to just print out hi, and then that's the end of it. Yeah. If I did this with hellos.txt, it would print out like all the lines of that file. I forget how many lines I put in there, 10 or something.
I guess I didn't know how cat was implemented, so I didn't know like if it would just do that or if I had to pass an argument to the file descriptor.
You can pretty blindly assume for this assignment that we're going to run cat like this with input redirection. We're never going to pass it a file name, and the reason for that is mainly 100% that the version of cat that we're actually running with has no idea how to read files from the volume. If you, for example, were to run cat readme.md in your shell, this will coincidentally work in some cases because it will try to open readme.md and it happens to be in the same directory outside the volume, and it'll work. It's unexpected, but it will work within the context of us evaluating your shell. If we're running cat, the only way we're going to run it is like this, with no file names and no input redirection, or with input redirection explicitly. So we're never going to expect you to support reading from a file name. It will coincidentally work, but that's not what we're expecting. Yeah. Okay, thank you for clarifying that. Should commands like echo be able to echo anything or only stuff from standard input? So I want to clarify echo, because I've seen this a couple times on the forum, and I want to make sure that we're clear about this. Echo as a command doesn't read anything on standard input. Echo only takes input on the command line. So if I say something like echo hello on the command line, it prints out hello. If I type in echo and then readme.md, it doesn't print anything. And it doesn't print anything because we are successfully redirecting the input, standard input for this program to be readme.md, but echo never reads anything. It never tries to call read on any file descriptor. It never tries to call open on any file descriptor. It just takes whatever was passed into argv and it prints that on standard output.
When it comes to input redirection, can we expect there's going to be one thing that's going to generate the output, and then the other thing which will be directed to? There's not going to be like multiple.
so there could be multiple pipes. So I could say like echo, and then hello, and then cat, and then sort, something like that. That is possible for me to do something like that, yes. Yeah. So something like this would still just print out hello because I'm printing out standard input back to standard output and then sorting it, but it's only one line, so it's just going to print out that one line. Okay. I was trying to do the launch process, and I saw online that examples use mfd clo-exec. Can we use that? So I would advise against this. I would advise against this because, explicitly because all the programs in the root volume are shell scripts. And if you read the manual page for mfd create and open and fexecve, it actually explicitly calls out the circumstance where we're using a shell script, and it describes that by the time the program eventually gets to run, the shell script will have been closed, and then it can't read it. So I wouldn't use this. I didn't need to use this when I was implementing my own stuff. All right, so it is a little bit past time, so I'm going to pop back over here. At this point, you should be able to write code that uses pthread mutex lock to protect a critical section, and you should be able to have some thought about where we put those locks. So we saw with this thread insertion example that there's a bunch of places that we could put it, but there's different consequences for putting it in each of those locations in terms of how much concurrency we're able to accomplish. At this point, you can't really do anything with identifying code protecting a critical section that would result in deadlock. You should have some sense of what deadlock requires, and you should be able to look at that code and say that maybe deadlock happens here, but that's kind of where we're at right now. I hope that you all have a good rest of your day, and I will see you all on Wednesday. Bye, everyone.